No, but it's like I'm trying to see how.
So we are going to do, or kind of get an insight into the empirical rule of normal distributions. The reason why I did Chebyshev theorem is that this particular distribution will prove that that theorem is true, but in general, pretty much every distribution is going to satisfy that theorem. So what does the rule state? If you have a data that has a bell-shaped histogram, X bar is the mean, and what is S? Standard deviation. So let's say S is the standard deviation, it's given to us. Then those lines would correspond to X bar plus S, X bar plus 2S, X bar plus 3S. So from the mean, you take one step forward proportional to or equal to a standard deviation. So you're not just moving by one step or 1 unit, you are moving by S units. S is defined by the standard deviation. That's on the right hand side. On the left hand side, we have X bar minus S, X bar minus 2S, and X bar minus 3S. Good. If that is the case, the case one, if you are within one standard deviation from the mean, yes, 60%. It is. This would be 68%. But then 2 standard deviations from the mean, in the sense from here you're going there. Do you expect this number to go up or go down?
Up.
Up. So from 2, we are going to 3. So do we expect that number to go up or down? Up. And this will be 99.7%. These numbers these percentages are not going to change. As long as the data has a frequency, a histogram that resembles a bell-shaped curve or bell shape, then these numbers will remain the same. So 68% within one standard deviation from the mean, 95% 2 standard deviations from the mean, and 99.7% 3 standard deviations from the mean. Good. So these numbers don't change, which is why we call this the empirical rule of normal distributions, because normal distribution will satisfy this. Last time we looked at Chebyshev theorem, and the theorem stated that k cannot be equal to 1. K is the number of standard deviations we're going to take. So what percent of observations will lie within k standard deviations from the mean, according to the theorem? You can look at the notes. What percent of observations will lie within k standard deviations from the mean?
1 minus 1 over k squared.
1 minus 1 over k squared times 100%. Yes, that's from last time. And it's not exact, the keyword here is at least. That's a math. And k cannot be equal to 1. So let's see if that guy was right. I mean, even if it's wrong, doesn't matter, he's dead. He doesn't care. But he's right 100%. So there is a proof for it too. Now, this is what I want you to do. So from here, I move 2 standard deviations. Yes. So k would be equal to 2. So plug it in that formula of k equals 2 in there and tell me what percent you get. Likewise, if you go 3 standard deviations from the mean, what is the value of k? If you go 2 standard deviations from the mean, k is 2. If you go 3 standard deviations from the mean,
3.
k is 3. Okay, so plug in k equals 2 and tell me what you get. Then plug in k equals 3 and tell me what you get in that form. Okay, what do we get for k equals 2? 75%. We did that last time. So according to the theorem, it is 75%. Not exactly, but at least 75%. So 95% is definitely bigger. So that's right. When you plug in k equals 3, what do you get? 88.888, which is 88.89%. So the theorem states that it would be at least 88.88%, and we have 99.7%. So the guy was right.
When you multiply by 100, like what? How do you multiply that in a calculator? Is it 0.10?
Just times 100.
Oh,
So if you have point
but
parentheses, we'll put parentheses. We have average utility bills monthly. $70 is the mean, $8 is the standard deviation. The question is between what 2 values do about 95% of observations lie. What the assumption that they make in the problem is the sample is normally distributed. In the sense, it has a bell-shaped histogram. If that is the case, we can use the empirical rule. And what does it say? Within 2 standard deviations, we will have 95% of the observations. Do you agree? Yes. So they want to know what are the 2 values to about 95% of observations lie. It has to be within 2 standard deviations from the mean, based on the rule. So the mean is 70. 2 standard deviations from 70 is 86. And to the left, 54. Most common mistake, people would just add and subtract, 2. That's not right. 2 standard deviations to the right, 2 to the left. So 2 times 8 would be 16. 70 plus 16 is 86. 2 times 8 still 16. 70 minus 16 is 54. Does that make sense? So between 54 and 86 dollars, you'd have 95% of the observations. So if I go to this city and if I picked 100 households, approximately how many of them would have an average monthly utility bill between 54 and 86? 95, because 95% of 100 is 95. That makes sense.
Can you repeat that again?
So if I went to the city where this data was collected, and if I looked at 100 households based on this data, how many of them would have an average monthly utility bill between 54 and 86? Since 95% would lie between 54 and 86, what is 95% of 100? 95. That makes sense. So according to the book, probably is correct. So they got this information using that sum. So they used those numbers, took the average, they got 70. Use those numbers, average standard deviation happens to be 8. We know how to find the mean and the standard deviation using the calculator. If you tried it, hopefully you get 70 and 8. So the question here is, are any of the observations unusual or very unusual? Can I erase this? Yes. The data, again, is normally distributed because this particular problem is related to the previous one. So we want to know if any of the observations there are unusual. We typically call an observation to be unusual if it falls outside the 95% limit. We call it unusual, very unusual, if it falls outside the 99.7% limit. We already know from the previous problem the percent of observations that fall between 54 and 86 last time, last problem, which was 95%. I want you to find the two values between which you would have 99.7% of the observations. Okay, so 3 standard deviations from the mean. We already know 2 standard deviations. So what is that number and that number?
That was mine.
94 and
46.
46. So within those 2 points, what percent of observations will lie?
99.7.
99.7%. And I mentioned earlier, typically we call it unusual if it lies outside the 95% limit. So, and very unusual if it lies outside the 3 standard deviation limit. So are there any observations that are outside the 3 standard deviations limit? 98. So that observation falls here. Yes. And is there an observation that is unusual? 52. Yes. Oh, wait. Good. Mind you, these are simply initial ways or analyses or inferences that you would make at the very beginning. After this, of course, there are other ways to determine, with a good probability if something is unusual, usual, and so forth. Are we clear? Yes.